Okay, so we're going to start with one of our rules for continuity, our theorems. If f of x is continuous, then f of x raised to the n power is also continuous. All right, so let's go ahead and look at our function. If I have f of x is equal to x minus 5 to the third power, and remember that can also look like x minus 5 to the 1/2 power raised to the third. You may also see this originally written as x minus 5 to the 3/2 power. The idea behind this is we've taken it and rewrite the functions so you have one function inside raised to the other side. This 3 in this case is n. So what I have to do at this point is I look at the inside function and ask, where is this continuous? So I know that x minus 5 has to be greater than or equal to 0. So x must be greater than or equal to 5. What that looks like is going to be the square root function over here at 5. That is filled in, and it goes like this. This graph is only the graph of x minus the square root of x minus 5. Where is this graph? The inside. Remember, all of this that I'm talking about here, this is all my inside function. And then this graph, we talked about left-hand continuous, right-hand continuous. This graph is continuous going from 5 all the way up to positive infinity. Now, this is what the theorem says. If this is continuous, then that function to the n is continuous. So we can go ahead and conclude that f of x of x minus 5 to the 3/2 is continuous about that same interval. All right, so we're going to do the same thing. We're going to break this up into the radical portion and rewrite that as x squared plus x plus 2, all raised to the 1/3 power. And they're going to raise this to the 8th. So the graph of my inside function is the cubed root, of x squared plus x plus 2. Now, this is interesting because remember, hopefully, that whenever you have x to the third, this is fine. There's no points inside here that is going to go ahead and give me a problem because you're allowed both positive and negative numbers underneath that cubed root. So the inside function is continuous from negative infinity to positive infinity. So because I am taking this inside function and raising it to the 8th power, that's going from my f of x raised to the n, which in this case, g of x is equal to x squared plus x plus 2 to the 8/3. It has the same continuity of that inside function, which in this case is negative infinity to positive infinity. Now, to summarize all of that with a rule, if you have any function raised to the 1 over n, we break it down into two conditions. If n is even, these are our conditions. Then we know that f of x is continuous. At all points. Where f is continuous and f of a is greater than 0. You're going to have to look at the right-hand part of continuity at 0 to decide the 0 portion. Now, the nicer one is if n is odd, and if n is odd, then it is continuous at all points where f is continuous. All right, so let's go ahead and look at this example of f of x is equal to 16 minus x squared. And again, I do like always drawing these pictures. I do recommend taking the time to graph these out, especially if you're having, if it helps you to go ahead and see those. So this is a graph of a half a circle. And we're going to fill in some of these missing pieces, but just to give you an idea, this is what we're looking at. Now, what we have inside here is f of x is equal to 16 minus x squared to the 1/2 power. So we know if we look at the inside function, where is that continuous? And that is x squared minus 16x is continuous for all values from negative infinity to, what does our definition say though? It says that this will be continuous when 16 minus x squared is greater than 0. We'll have to check the limit parts for both ends. All right, so where does that happen? That happens when 16 is greater than x squared. You have to set this up with an inequality and make this from 16 is greater than x squared, which is less than negative 16. Take the square root of all of it, and you get it's between 4x and so this means from our theorem right now, we know that it is continuous from -4 to 4. Now we have to see, looking at the right-hand side and left-hand side, if -4 and 4 are included. It does appear to be so. -4. All right, which is what we have shown up here. Now, let's test some different points to find out if it is equal to 0. We need to know a couple of things. We need to know what happens of f of -4, and we need to know what happens at f of +4. And the question is, does that equal the limit as x approaches -4 of our function? And does this equal the limit as x approaches +4 of my function? And the -4 is going to be, we're going to have to look at the positive and negative sides of that. All right, so at f of negative 4, that just equals the square root of 16 minus negative 4 squared, or 16 minus 16, which equals 0, which I already have that point over here. The same thing is true, and we can see that f of 4 is also equal to 0. So going back to where we have with the limits. At negative 4, we are coming in from the right-hand side. So we are coming in at negative 4 from the positive side. And yes, as I'm coming in from negative 4, it does approach 0, which matches our limit. So I can go ahead and say, yes, this is equal to 0. So this point, I can go ahead and say this is yes, and this is included. I say the same thing for the next one. Again, this is the limit as x approaches 4, but for this one, we are coming at it from the negative side, and that negative side and that negative limit still equal 0. This is equal to 0, so this point is also included. So the final piece, we know that f of x is continuous on negative 4 to 4.